If you went looking for wall-to-wall coverage of 3 Atlas, you'd probably expect live space agency streams, bold press conferences, or big science headlines. After all, this is only the 3rd confirmed interstellar visitor in human history. But instead of a broadcast, the public has been left with breadcrumbs. Tiny fragments scattered in technical reports and archived updates. One breadcrumb arrived when astronomers quietly confirmed the official designation: 3 Atlas C225N1, making it clear this object was not born in our solar system. Another came a few weeks later, when telescope data suggested the nucleus was smaller than 6 kilometers across, details tucked away in dry logs rather than headlines. Then came a preprint with chemistry results. The comet's coma appears to be dominated by carbon dioxide at a ratio far higher than water ice, a finding almost unheard of in known comets. And finally, a short mission note. Spacecraft orbiting Mars would aim their instruments at 3I Atlas during its October 3rd flyby. No bold graphics, no live stream countdowns, just plain technical language. And then, silence. No major announcement, no dramatic animations like the ones that greeted a Mars rover landing or the asteroid deflection mission. Just crumbs on the table. That silence is where the paradox begins. Because when institutions decide to speak softly, the gaps fill themselves. A dry note about gas chemistry feels like a hidden warning. A single line about observation campaigns reads like something deliberately understated. Even the pauses between updates start to feel intentional, as if the quiet itself were part of the story. This is how human history has always worked. Sailors once filled blank regions of maps with dragons. Chroniclers turned gaps in records into myths. And in 2025, the same reflex applies. Silence doesn't calm curiosity, it multiplies it. Each missing word becomes a doorway to speculation. So, while the agencies scatter breadcrumbs, it's amateurs, independent observatories, and outspoken voices who are telling the story most people actually hear. They post raw images showing unusual tails and brightness flickers. They speculate openly where institutions hesitate. And because their narrative comes with urgency instead of caution, it spreads further and faster. The question is not whether the crumbs are real. They are. The question is why the people who usually put on a show decided this time to stay quiet. And when all the public is handed are breadcrumbs, what kind of story do we inevitably weave to connect them? That is where the mystery of 3 Atlas truly begins. If someone scripted this moment as a movie, the tension curve would be perfect. A rare object from another star system enters, brushes past Mars, heats up near the Sun, and then vanishes into a window where our telescopes go blind. The timing is cinematic. The plot beats are flawless. Maximum drama, and yet the official voice, minimum noise, instead of the sweeping animations and press briefings that usually accompany space milestones. What we have are technical memos, occasional blog notes, and observational updates buried in databases. A single line about perihelion geometry. A chart with no context. An archive upload with more equations than explanation. That's it. Contrast that with how the same institutions treated past events. The Mars rover landing, the asteroid impact test, or the first images from a space telescope. Those were turned into spectacles, live streams, hashtags, even countdown clocks. But with 3 Arj Atlas, the third interstellar visitor ever recorded, threading directly past major planets, the spotlight is missing. The silence itself becomes louder than any announcement could be. And here's where the psychology of storytelling kicks in. A blackout period caused by the sun's glare is a simple geometry problem, but to the public, it feels like the setup of a thriller. Just as the object reaches its most interesting stage, our view is cut off. The institutions describe it as a solar conjunction. The audience hears it as cover-up. This mismatch, maximum drama in the sky, minimum drama in the press, creates a vacuum. And vacuums demand to be filled. Into that gap step, amateurs with smart telescopes, independent researchers posting raw images, and contrarian scientists who aren't afraid to speculate. Their voices are unfiltered, fast, and dramatic. And because they speak with urgency instead of restraint, their narrative spreads far wider than any quiet agency blog ever could. The silence doesn't mean nothing is happening. It means the story is being written elsewhere by those who dare to frame it with mystery. And when official channels give us minimum noise during maximum drama, the loudest story becomes the one told outside the institutions. Every mystery needs a locked room. For 3i Atlas, that locked room is the sky itself. As the object races toward its closest point to the sun, our instruments on Earth hit a hard limit. It isn't politics, it isn't budget, it's geometry. Telescopes cannot aim too close to the sun without frying their detectors, and even if they could, the glare would overwhelm the faint light of a comet's nucleus and coma. From late October into November, just as 3 Atlas experiences its maximum heating, Earth-based observatories are forced to look away. This means the most critical moment, the perihelion window, when gases erupt, when structures shift, when hidden chemistry is revealed, will happen in near darkness from our perspective. It's not that nothing can see, it's that we can't. The only eyes still open during this blackout are not ours. Spacecraft in orbit around Mars will have a partial view. Solar observatories designed to stare at the sun may catch glimpses of broad dust plumes, but not the fine chemical details. For most of humanity, the feed cuts to static just as the drama peaks. This is how suspicion grows. A scientist may calmly explain solar conjunction, a simple alignment that blocks line of sight. But to the audience, it feels like the timing is too perfect. An interstellar object threads through our planetary neighborhood, behaves oddly, then slips into a period of forced invisibility. It reads less like an orbital inevitability and more like an act in a play. And the danger of a blackout isn't just that we can't see, it's that the silence will be filled with substitutes. In the absence of official images, expect anonymous uploads. Expect leaks claiming to come from spacecraft archives. Expect video clips of streaks and artifacts framed as revelations. Some will be genuine, others faked or misattributed. But during the blackout window, the ability to separate one from the other collapses. When the curtain finally rises in December and Earth regains its view, the public will already have made up its mind. By then, a dozen stories will be circulating, some plausible, some wild, and all of them louder than the cautious explanations that follow. The truth might arrive, but it will be competing with weeks of speculation that already feel real. This is the paradox of 3 Atlas. The very physics that make it most fascinating, an interstellar trajectory, a sun-skimming orbit, also guarantee that for the most dramatic act, the main stage goes dark. Not because anyone flipped a switch, but because the laws of light and gravity demand it. For scientists, the blackout is a frustrating inevitability. For storytellers, it's rocket fuel. And for the rest of us, it's an uncomfortable truth. Sometimes the universe itself conspires to keep its secrets hidden, at least until the curtain opens again. The final ingredient in the mystery of 3I Atlas is not its chemistry, or even its strange trajectory. It's the timing. Think about the sequence. The object is first spotted just as it begins slipping into the inner solar system, too faint for most of the world to notice. By the time the orbit is calculated and the interstellar origin confirmed, it is already weeks away from its first planetary encounter, Mars, in early October. That moment, the closest approach to another world, happens just before the object passes behind the Sun from Earth's point of view. In other words, our best telescopes are blinded right after the first close flyby. From there, the narrative writes itself. On October 30th, at perihelion, the comet reaches peak solar heating, the time when hidden ices crack, jets erupt, and internal structures reveal themselves. But Earth cannot watch. The geometry makes us turn our heads. We only reacquire the object weeks later in December, when the most interesting phase has already passed. This coincidence, close encounters, strange chemistry, sudden invisibility, lands with a suspicious rhythm. To astronomers, it's simply orbital dynamics. To the public, it feels staged, like a curtain drop, timed for maximum suspense. And timing doesn't exist in a vacuum. While 3I Atlas is slipping behind the Sun, other headlines are unfolding. Defense meetings with vague agendas, year-end government reviews, shifting news cycles. People notice overlaps. 2 unrelated events placed side by side start to look connected, even when no evidence links them. That's the danger of timing. It doesn't need proof to make a story. It only needs proximity. History shows this pattern again and again. A solar eclipse coinciding with a king's death becomes an omen. A comet appearing in the sky during a war becomes a prophecy. When cosmic timing overlaps with human events, interpretation fills the gap. And in the digital age, that interpretation spreads faster than the official explanations ever can. So, when agencies stay quiet, when the geometry forces blindness, when the most dramatic sky events align with silence on Earth, suspicion multiplies. Not because the data is wrong, but because the calendar feels too perfect. This is why timing matters. It shapes not only what we can observe, but also how we interpret it. The blackout window ensures that speculation peaks precisely when information is scarcest. And when the object finally re-emerges in December, the truth, whatever it turns out to be, will have to compete with weeks of stories already written in people's minds. 3I Atlas. May be a comet. It may be exotic. It may be nothing more than an icy traveler from another star system. But the timing of its journey guarantees one thing. The mystery around it will outpace the science. Every story needs an origin point, And for 3I Atlas, that moment came on a quiet night in early July 2025. A sky scanning system in Chile picked up a faint, moving point of light. At first, it looked like nothing unusual, just another entry in the endless stream of small bodies drifting across the heavens. But within hours, calculations began to show something extraordinary. The orbit was not the gentle ellipse of a planet, nor the stretched oval of a long-period comet. This path was open, hyperbolic, screaming that it did not belong to our sun. Its eccentricity, the measure of how stretched an orbit is, was greater than 1. That simple number told the entire story. This object was unbound, passing through once, never to return. Within a day, the discovery was confirmed by multiple observatories. The official designation followed: 3I Atlas 25N1. The C indicated cometary activity, a fuzzy coma already forming around a hidden nucleus. The I marked it as interstellar, the third of its kind ever verified. Only 2 others had been confirmed before: 1I Oumuamua in 2017 and 2I Borisov in 2019. Now came a third, sliding into history. The speed was staggering. Relative to the Sun, 3 Atlas was barreling inward at about 61 kilometers per second. That's over 200,000 kilometers every hour, fast enough to cross the distance from New York to Los Angeles in less than a minute. Unlike spacecraft, which achieve such speeds only with the help of planetary slingshots, 3 Atlas carried this velocity from the interstellar void itself. It had been traveling, uninterrupted, for millions of years. The designation itself might seem like bureaucratic formality, but within those few letters lies the scale of the event. 3 interstellar objects in all of recorded human history. That's it. Countless asteroids and comets catalogued, but only 3 traced back beyond the Sun's domain. It's as if Earth had been a quiet village for millennia, and only now, once every few years, a stranger passes through carrying dust from another world. Yet, for such a historic moment, the announcement came with little spectacle. A dry notice, a technical circular. No breathless media storm, just confirmation that a visitor from the stars had entered our neighborhood. This is how the breadcrumb trail began, not with a trumpet, but with a whisper. And here is where the tension forms. We know how institutions respond to discoveries with drama potential. They mobilize, amplify, celebrate. But with 3I Atlas, history's third confirmed interstellar wanderer, the curtain barely stirred. Perhaps that restraint is caution. Perhaps it's bureaucracy. Or perhaps silence itself was part of the script. But one thing is certain. From the moment of discovery, the story of 3I Atlas was marked not just by its trajectory through space, but by the way its entry was framed. Quiet, clinical, easily overlooked. A cosmic traveler slipping past the headlines, even as it slipped into history. Once 3 Atlas was confirmed, its path through the solar system could be traced with unsettling precision. Anyone with the right software could generate the same predictions that astronomers were quietly posting online. The numbers weren't hidden. They were there for anyone willing to look. And those numbers told a story almost too elegant to believe. The orbit is hyperbolic, open, unbound, never returning. That means it's not just another icy fragment from the Oort cloud. shaken loose by a passing star. This is an outsider, its velocity too high for the Sun to ever reel back in. 61 kilometers per second inbound. At that speed, the object will pass through our system in mere months, not the centuries or millennia we expect from long-period comets. The geometry is what captures attention. Instead of plunging through at a steep angle, like a stone skipping off water, 3 Atlas is sliding in almost along the plane of the planets. Only about 5 degrees off the ecliptic, the flat disk where Earth, Mars, Venus, and Jupiter trace their orbits. Out of all the infinite angles in three-dimensional space, this visitor chose the highway. Statistically possible, yes. Probable? Far less so. The timeline makes the story sharper. On October 3rd, 2025, it brushes past Mars at a distance of about 30 million kilometers. In cosmic terms, that's a hair's breadth, a chance alignment that gives orbiters around Mars a perfect vantage point. From there, it dives inward, reaching perihelion on October 30th, at roughly 1.5 times Earth's distance from the Sun. Not a death plunge into the solar furnace, but close enough for its surface to crack and boil. The sequence doesn't end there. After perihelion, it sweeps past Venus in November, then makes its closest pass by Earth in December. Never threatening impact, but still within range to be studied. Months later, it drifts past Jupiter's orbit. 4 planets in sequence, 4 opportunities for observers. One trajectory threading them all. For astronomers, the orbit is proof of what it is. Interstellar, unbound, another piece of alien real estate passing through. But for the wider world, the path itself feels uncanny. It looks less like a random plunge through the solar system and more like a plotted course, a grand tour through the inner planets. Rationally, the mind says coincidence. Viscerally, it whispers intent. And yet, the numbers are public. They can be checked by anyone. Plug the designation into an orbital calculator, and the same plot will appear. The sharp, hyperbolic curve, the sequence of planetary encounters, the outbound arc vanishing back into the dark. No secrets, no hidden equations. The orbit is in plain sight. The question isn't whether the path is real. It is. The question is how such an improbable geometry came to be, and why the official voices that know this orbit best seem reluctant to highlight the most striking parts of the story. When 3 Atlas was first spotted, the natural question followed. How big is it? After all, size determines mass, and mass determines how much influence an object has on its surroundings. But here's the problem. Nobody has seen the nucleus directly. What we see instead is the coma, the glowing halo of gas and dust released as the sun's heat begins to vaporize its frozen surface. From that light, astronomers model what the solid body inside might be. The results are estimates, not measurements, and they come with enormous uncertainty. One early calculation set an upper limit, no larger than about 5 to 6 kilometers across. That's not small. A 5-kilometer nucleus carries enough mass to hold itself together against rotational breakup, a respectably sized comet by solar system standards. But the same data could also fit a nucleus only a few hundred meters wide, closer to the size of a rubble pile, fragile, barely bound. The difference between those two scenarios is night and day. A 5-kilometer interstellar comet is a massive, long-lived traveler, capable of carrying unique chemistry for millions of years without breaking apart. A smaller, loosely held nucleus might be prone to sudden fragmentation, unpredictable jets, even complete disintegration during perihelion. The truth lies somewhere inside that range, but for now, we don't know where. Brightness complicates things further. The coma reflects sunlight, but how reflective is it? If the surface is darker than assumed, the nucleus could be larger. If it's unusually bright, it might be smaller. Add in the fact that some of the glow comes from dust, not just gas, and the models wobble even more. This lack of certainty feeds the mystery. The public hears 5 kilometers and imagines a mountain of alien ice. Then they hear a few hundred meters and picture a fragile shard drifting in from another star. Both are possible. Both fit the data. And because no telescope can yet resolve the nucleus itself, both remain in play. It's not the first time an interstellar visitor has kept its secrets. The first, discovered in 2017, was famously described as cigar-shaped, then later pancake-shaped, depending on which model fit the limited data. The second, spotted in 2019, was more cooperative, clearly cometary, easier to pin down. But even then, size estimates were fuzzy. With 3-eye atlas, history repeats, clarity in trajectory, uncertainty in mass. And here lies the irony. The single most basic question, how big is it, remains unanswered. We know where it's going. We know how fast. We even know what gases dominate its coma. But the nucleus itself, the beating heart of the visitor, is still hidden inside its glowing shroud. So the story continues in a blur of uncertainty, a traveler that could be a mountain or a shard or something in between. And until sharper data arrives, that uncertainty isn't just science. It's fuel for the mystery that surrounds it. If the orbit raised eyebrows, the chemistry blew them wide open. When the first spectroscopic data came in, astronomers expected the usual profile: water vapor dominating, with some carbon dioxide and carbon monoxide as secondary players. That's the recipe for most comets in our solar system. Ice and steam with a little fizz. But 3 Atlas didn't play by those rules. Instead of being water-rich, it turned out to be carbon dioxide heavy. Not slightly, not marginally, overwhelmingly. The ratio of CO2 to water was measured at roughly 8:1. Imagine opening a bottle expecting plain soda water, only to be blasted by pure carbonation. It wasn't just unusual. It was almost backwards. Why does that matter? Because volatile chemistry is the fingerprint of an object's birthplace. In our solar system, comets form in icy reservoirs far from the sun, where water ice is abundant and stable. CO2 is present, but rarely dominant. For 3I Atlas to be this skewed suggests it formed in a very different environment. Maybe around a colder, dimmer star, where carbon dioxide could freeze out more easily. Maybe in a region of its birth system's protoplanetary disk that was unusually rich in carbon. Either way, it looks less like one of ours, and more like a chemical stranger. And the surprises didn't stop at carbon dioxide. Alongside it were traces of carbon monoxide and more exotic molecules like carbonyl sulfide, a rare species even in the most well-studied comets here at home. Each chemical adds another piece to the puzzle, suggesting not only an alien origin, but also a formation history distinct from anything we've catalogued before. Skeptics argue there could be simpler explanations. Perhaps the water ice is still there, but buried deeper beneath the surface, shielded from the sun's early heat. Carbon dioxide sublimates at lower temperatures than water, so what we're seeing could just be the first layer venting. If that's the case, then after perihelion, when solar heating cuts deeper, the water signal might rise and balance the ratio. That's testable, but until we see those post-perihelion spectra, the imbalance stands. Another possibility: the nucleus isn't uniform. Some areas may be rich in CO2, others in H2O. As the object rotates, different sides vent at different times, producing temporary chemistry that looks stranger than it really is. That, too, would be consistent with the odd brightness flickers already observed. Still, even with caveats, the sheer dominance of carbon dioxide is startling. It turns a comet into something more like dry ice than frozen water, a body fizzing with alien chemistry. And while scientists are careful to avoid grand claims, history shows how anomalies like this change the narrative. First, we called it just another comet. Then, we measured its gases. Now, suddenly, we're confronted with a visitor whose internal recipe seems utterly unlike our own. If orbits tell us where an object came from, chemistry tells us how it was made. And in the case of 3I, Atlas, the chemistry doesn't whisper ordinary. It shouts, different. That difference is what makes the object not just a traveler through space, but a messenger from a place with rules we don't yet fully understand. Every good mystery has a chapter where the lights go out. For 3I Atlas, that chapter is written into its orbit. Just as the object grows most active, just as the sun's heat forces hidden chemistry to the surface, our line of sight collapses. From Earth's perspective, late October into November is a blackout window. The object passes too close to the sun in the sky, making it impossible for ground-based telescopes to point safely in its direction. Even if they could, the glare would drown out its faint glow. The timing could not be more frustrating. The moment of maximum heating, maximum venting, maximum change coincides with maximum blindness. This isn't conspiracy, it's physics. It's the same reason planets disappear behind the sun during conjunction. But when it comes to an interstellar visitor, the third in history, the effect doesn't feel like bad luck. It feels like a vanishing act. Other instruments will still be watching, but they're limited. Mars orbiters have a brief window to catch spectra during the early October pass. Solar observatories may detect broad plumes during perihelion, but they're designed for monitoring coronal mass ejections, not comet chemistry. The most powerful infrared and optical telescopes on Earth and in Earth orbit will be effectively blind. For weeks, the trail goes dark. And here's the danger of darkness. It doesn't just hide the object, it amplifies imagination. In the gap, expect anonymous images to circulate. Expect claims of hidden jets, broken fragments, strange alignments. Some may be genuine observations from smaller observatories, lucky enough to catch an angle. Others will be misinterpretations or outright fabrications. In the absence of official updates, everything starts to look like a revelation. By December, when the object emerges from solar glare, it will already be outbound, cooling, quieting. We'll pick it up again, but only after the most revealing stage has already passed. What did we miss? Did hidden water ice suddenly erupt? Did the nucleus fracture? Did the composition change in ways we'll never fully reconstruct? The gap guarantees that some questions will remain unanswered forever. This pattern isn't new. The first interstellar visitor teased us with strange motions that we couldn't fully explain, largely because it was faint and fleeting. The second was brighter, easier, but still gone too quickly for complete certainty. Now, with the third, we face the same frustration, just with a twist of orbital geometry that makes the silence feel deliberate. The observability gap isn't the product of a decision. No one chose to turn off the cameras. It's the inevitable result of where the sun happens to be. But history tells us perception matters as much as physics. Silence during peak drama always looks suspicious. And when the lights come back on, the story people have told themselves during the blackout will already have momentum. 3i Atlas will reappear in December. By then, we'll have data, but we'll also have weeks of speculation, rumor, and imagination layered on top. In many ways, the mystery is not just about what we can see, but about what we can't. When astronomers analyzed the gas streaming off 3i Atlas, the numbers didn't just raise eyebrows, they broke expectations. In nearly every comet studied within our solar system, water vapor is the dominant volatile. Carbon dioxide and carbon monoxide appear too, but usually as minor partners, maybe 10 or 20% of the water signal. 3i Atlas turned that pattern upside down. Its coma isn't water-dominated at all. It's overwhelmingly carbon dioxide. For every molecule of water vapor, there appear to be about 8 of CO2. That ratio is extreme, almost inverted compared to what we've catalogued here at home. So what could explain it? One possibility is origin. Comets inherit their chemistry from the environment where they formed. In our solar system, water freezes readily beyond a certain distance from the sun, the snow line, while carbon dioxide only condenses in colder, more remote regions. If 3 Atlas was born around a dimmer or colder star, its building blocks might have favored CO2 over H2O. In that case, what we're seeing isn't a trick of observation. It's a chemical fingerprint from another system entirely. Another explanation is depth. Maybe water is there, but buried. Carbon dioxide sublimates or turns to gas at much lower temperatures than water ice. As the comet approaches the sun, the shallow CO2 layers vent first, flooding the coma. The deeper water ice could still be locked inside, waiting for perihelion to heat the nucleus enough to reach it. If that's true, we may see the water signal rise in December, once the crust is thoroughly baked. Until then, the comet looks carbon-rich, even if its interior tells a more balanced story. A third possibility is patchiness. These bodies aren't uniform spheres. Their surfaces are scarred, fractured, irregular. Some regions could be rich in CO2 ice, others in water. As the nucleus rotates, different patches vent at different times, creating temporary dominance of one volatile over another. From Earth, that looks like a comet breathing carbon dioxide, when in reality, it's just showing us one side of a far more complex face. No matter which explanation is true, the sheer scale of the imbalance sets 3i Atlas apart. We've seen comets that were unusual, rich in carbon monoxide, or dusty beyond expectation. but rarely one so chemically lopsided. It suggests we're peering into conditions that don't exist in our own backyard, conditions that shaped ices in ways our sun's neighborhood never did. And here's what makes that important. Chemistry is history. Orbits tell us where an object has been. Chemistry tells us where it was born. A carbon dioxide-dominated comet is like a bottle of mineral water drawn from a spring on another world. The ratios are its signature. They don't just mark it as alien, they hint at the environment of the star system it once called home. Whether buried water emerges later or not, the message is clear. 3I Atlas is carrying a recipe written far beyond our sun, and for the first time in history, we have a chance to taste what another star system might be made of. If the chemistry of 3I Atlas is unusual, its behavior is even stranger. A normal comet brightens smoothly as it approaches the sun. The sunlight warms its icy surface, the gases sublimate, dust is carried along, and the coma gradually expands. It's a steady climb, a predictable curve. 3I Atlas doesn't follow that curve. Instead, observers report flickers, sudden changes in brightness, short bursts of activity, then lulls. To the naked data, it looks less like a steady crescendo and more like a pulse. Almost as if the comet is breathing. What could cause that? The most likely explanation is jets, streams of gas and dust erupting through cracks in the nucleus. If the surface is patchy, with some regions rich in volatile ices and others inert, rotation brings those active spots in and out of sunlight. One face vents carbon dioxide in a surge, brightening the coma. Hours later, as the nucleus spins, the jet disappears and the brightness falls again. The cycle repeats, creating a flickering heartbeat across the sky. But the flickers aren't always clean. Some observers describe sudden spikes, brighter than rotation alone can explain. That suggests outbursts, internal pressure building under a crust of dust until the surface ruptures. For a few hours, the comet vents violently, releasing more material than usual, then settles back down. Imagine a kettle whistling and sputtering as steam forces its way through clogged valves. Another possibility is structural weakness. If 3 Atlas is small, closer to a few hundred meters than a few kilometers, its nucleus could be fragile, a loose pile of rubble held together by weak gravity. As heat penetrates, pieces shift, fractures open, gases escape unpredictably. The object becomes less like a solid body and more like a breathing sponge. To an astronomer, this is fascinating physics. To the public, the imagery is uncanny. A visitor from another star system pulsing with irregular light, alive in a way rocks shouldn't be. It's not alive, of course. It's chemistry, rotation, sublimation. But the metaphor sticks. A breathing visitor, a heart of ice that beats when touched by the sun. And this behavior matters. Jets aren't just spectacle. They act like tiny thrusters, changing the object's trajectory. If one side vents more strongly than the other, the recoil can nudge the comet off its predicted path. Usually, the effect is small, but with interstellar objects, every anomaly gets scrutinized. A trajectory that shifts too much, or in the wrong direction, could hint at forces we don't yet understand. For now, the flickers remain within the realm of natural explanation. Patchy surfaces, outbursts, rotation, but they add to the growing list of ways 3I Atlas refuses to behave like the comets we know. It is faster, it is stranger, and it does not brighten like a simple block of ice. Instead, it flickers, it surges, it breathes. And in those breaths, we hear the unsettling reminder that we are watching something born under a different star, responding to our sun in ways we can only begin to decode. Every comet carries a tail, or at least that's what we're taught. Heated by the sun, gases and dust stream outward, forming a glowing trail that always points away from the solar glare. It's one of the simplest rules of comet physics. Radiation pressure and the solar wind push the material back, like smoke drifting downwind from a fire. So, when observers of 3I Atlas began reporting something that looked different, a plume pointing toward the sun instead of away, it sent imaginations racing. A tail against the rules. That would mean forces at work we don't understand, or perhaps even propulsion. The idea of a comet pushing itself sunward against the current has a magnetic pull on the imagination. But reality, as it often does, is more complicated and less dramatic. What many were seeing was an anti-tail, a well-known but easily misunderstood effect. Instead of being a separate stream of material, an anti-tail is an illusion of geometry. As the comet orbits, dust particles released earlier spread along its orbital path, forming a thin sheet. From certain vantage points, when Earth lines up with that sheet, the dust appears to project forward, toward the sun. It's not fighting the solar wind at all. It's just perspective. 3 dimensions collapsed into 2. This phenomenon has been observed before, though rarely, in some of the most spectacular comets of the past century. The effect can be striking, a sharp spike pointing in exactly the wrong direction. For casual observers, it looks like physics breaking in plain sight. For astronomers, it's a reminder that appearances in space are often deceptive. And 3I Atlas, with its nearly coplanar orbit aligned close to Earth's viewing angle, is especially prone to creating these optical tricks. The dust sheet lies almost flat in the same plane as the planets. That makes the geometry just right for anti-tails, false plumes, and apparent structures that look far stranger than they really are. This doesn't mean every anomaly is illusion. Jets can create irregular plumes. Outbursts can make the coma asymmetric. Small fragments breaking loose can leave temporary trails. But separating real structure from optical projection requires careful modeling. You need to account for angles, phase, and timing. Without that, a dust sheet seen edge-on becomes a sunward jet. A faint outburst looks like a solid fragment. A shadow in the coma becomes an imagined craft. The danger is obvious. In the age of instant sharing, raw images race across screens long before context catches up. A streak in one amateur frame becomes proof in a dozen forums. A sunward spike becomes a whisper of design. The optical gotchas of 3I Atlas risk becoming fuel for the most dramatic stories. Stories far harder to erase once they take root. Yet this too is part of the mystery, because even when you know the science, the illusion remains powerful. Our eyes are wired for patterns, for straight lines and symmetry. When the sky draws a spike in the wrong direction, our instinct is to say, that can't be natural. And maybe that's the enduring allure of 3I Atlas. It not only brings alien chemistry and strange behavior, it also bends light and perspective into shapes that look like secrets, even when the explanation is sitting in the math. The nucleus of 3I Atlas remains hidden inside its glowing coma, but the light it reflects still carries clues. Careful measurements reveal subtle fluctuations in brightness over time, a rhythm that betrays rotation. This object spins, just as every comet does, and its turning motion offers the first glimpse of what lies beneath the haze. But rotation alone doesn't explain the irregularities. The light curve isn't smooth. It flickers, stutters, and occasionally surges in ways that suggest something deeper. The likely culprit: heterogeneity. The nucleus of 3I Atlas may not be uniform, but patchy. Different regions rich in different ices, layered unevenly like a cosmic geological record. One face may vent carbon dioxide. Another may hold water ice. Others may be barren crust, dusty and inert. As the comet rotates, these contrasting surfaces come into sunlight, vent, and then rotate out again. The result is a complex rhythm of activity, as if the comet is speaking in bursts rather than in a steady hum. It is not a single frozen block, but a quilt of materials stitched together across eons of interstellar travel. Then there's the question of internal structure. Some astronomers suspect pockets, cavities of volatile rich material trapped beneath the surface. Imagine a layer of crust holding back a reservoir of frozen gas. As heat penetrates, pressure builds. When the crust fractures, the gas escapes in a sudden jet, brightening the coma for hours or even days. Once vented, the surface reseals with dust, and the cycle begins again. To the eye, it looks like breathing. To physics, it's pressure, fracture, release. These pockets could also explain the irregular outbursts already reported. A nucleus riddled with voids is not stable. It's fragile. That fragility carries risk. Smaller interstellar objects are particularly vulnerable to disruption. And if 3I Atlas is on the lower end of size estimates, a violent outburst could split it into fragments. History shows this is not uncommon. Many comets have torn themselves apart under solar stress. If this happens, the event could rewrite everything we think we know about its composition. But until it happens, we're left reading shadows. The light curve hints at irregular rotation, perhaps even tumbling, rather than spinning cleanly around a single axis. The coma's chemistry points to a patchwork surface. The brightness surges suggest trapped volatiles breaking free. Together, they describe a body that is not only alien in origin, but unstable in character. And here's the irony: instability makes it more valuable. A comet that cracks open reveals its interior. A fragmenting nucleus spills secrets that a stable one hides. If 3I Atlas is indeed riddled with pockets and layers, then every burst is a message, every surge a clue to the star system where it formed. For now, it is still whole, spinning irregularly, exhaling in uneven rhythms. But deep inside, the pockets are waiting, and as the sun continues to heat this ancient traveler, we may discover that its greatest secrets are not in what it shows steadily, but in what erupts suddenly, without warning, from within. Every mystery needs a control. With 3 Atlas, the question isn't only what makes it strange, it's also what would prove it's not strange at all. Because science advances, not just by discovering anomalies, but by showing when anomalies are illusions. Take the chemistry. Right now, the comet looks wildly carbon dioxide dominated, almost inverted compared to normal solar system comets. But that picture is based on early data before perihelion. If, after the closest approach to the Sun, water ice begins venting in large quantities, the ratio could balance out. What looks like an alien recipe might simply be a matter of timing. CO2 on the surface venting first, water trapped deeper, releasing later. If that happens, the weirdness dissolves into a natural explanation. Or consider the flickers in brightness. Some interpret them as breathing, pulsing, or even hints of instability beyond the ordinary. But brightness variations can also come from rotation combined with geometry. A lumpy nucleus spinning in sunlight will appear brighter at some angles and dimmer at others. If careful modeling shows that the light curve matches a rotating, irregularly shaped object, then the apparent strangeness collapses into normal comet behavior. The so-called sunward plume provides another test. For some, it looks like propulsion against the solar wind, an impossible structure pointing the wrong way. But if anti-tail modeling, geometry and dust projection matches exactly what observers are seeing, then the exotic interpretation evaporates. What looked like defiance of physics becomes an illusion of perspective. Even the trajectory, which some find uncanny, can be checked against probability. At first glance, a path that threads Mars, Venus, Earth, and Jupiter looks designed. But with enough interstellar objects, some will inevitably skim close to multiple planets. If surveys show that such alignments are more common than we thought, then the apparent mission profile loses its weight. Coincidence, not conspiracy, writes the orbit. The final check is non-gravitational acceleration. If the comet's path shifts in ways consistent with venting gases, then all the flickers and surges have a natural cause. If the accelerations exceed what the observed outgassing can explain, only then would the mystery deepen. But if the math balances, the extraordinary collapses into the ordinary. In short, there are ways for the strangeness to vanish. If water rises after perihelion, if flickers match rotation, if anti-tails match dust geometry, if the orbit behaves exactly as gas dynamics predict, then Atlas returns to the realm of comets. Still historic, still valuable, but no longer unsettling. And that's the razor's edge where this story lives. Right now, the data is incomplete, and incomplete data favors imagination. But the closer we get to December, the more tests become possible. Either the weirdness holds up, or it dissolves under scrutiny. If it dissolves, we have a comet. If it holds, we have something more. The truth lies in what survives the test of falsification, and until that test is complete, the mystery remains intact. One of the most unsettling things about 3I Atlas isn't just its speed or its chemistry, it's the path it chose. Out of all the infinite angles an interstellar object could take as it cuts across the solar system, this one arrives almost perfectly aligned with the ecliptic plane, the thin sheet where the planets orbit. The ecliptic is like the solar system's highway. Earth, Mars, Venus, and Jupiter all trace their orbits along it. Asteroids and comets born here usually hug this plane too. But interstellar objects? They don't belong to this family. They can enter from any angle, any inclination, because the galaxy doesn't line up neatly with the architecture of our Sun. Statistically, you'd expect most visitors to come in steep, skimming high above or plunging below the disk of planets. But 3i Atlas doesn't. Its orbit is only about 5 degrees off the ecliptic. That's razor thin, almost coplanar. It's like a car from another city merging into traffic and slipping neatly into the correct lane. For some, this geometry feels suspicious, too aligned, too convenient. If you wanted to visit a planetary system and study its worlds, this is the path you'd pick. A low inclination trajectory that threads close to multiple planets in sequence. It's a pattern that at first glance looks intentional. But here's where caution is needed. The human brain is a pattern-seeking machine. We are wired to see design where coincidence suffices. And in this case, there is a very real explanation that doesn't require hidden motives. Selection bias. Most of our sky surveys are not scanning the entire heavens equally. Telescopes prioritize the ecliptic because that's where the action is. Near-Earth asteroids, main belt comets, Trojan swarms, they all live close to that disk. Our search strategies reflect that. If you look mostly along the highway, you'll mostly find things traveling along the highway. Visitors coming in from steep angles might pass unnoticed, simply because we're not watching the skies where they move. This means the apparent alignment of 3i Atlas could be more about us than about it. We found it because it came where we were already looking. If it had entered 30 degrees above the ecliptic, the same object might have slipped by unseen. In that light, the coincidence isn't cosmic design. It's observational bias. But knowing this doesn't erase the unease. Because probability is not comfort. The odds of an interstellar object threading so close to Mars, then swinging toward Venus, Earth, and Jupiter in sequence are low. Low, but not impossible. And when the improbable lines up in plain sight, people reach for explanations bigger than chance. So the question becomes, is 3e Atlas a carefully plotted tour through the inner solar system, or just the first one we noticed, because it happened to enter on the plane where our eyes are already fixed? Both answers are possible. Both can be true at once. And until we understand how many interstellar objects are truly out there, every low-inclination visitor will look a little too much like a guest who knew exactly where the door was. When you trace the path of 3i Atlas across the solar system, the pattern looks almost deliberate. First Mars on October 3rd, then perihelion by the end of the month, then a close pass of Venus, a sweep past Earth in December, and months later, a brush near Jupiter. 4 worlds in sequence, 4 opportunities for observation. It doesn't just skim past our system randomly, it seems to tour it. If you were designing a reconnaissance mission, you might pick a path that does something similar. Use a Mars flyby to take a reading of a thin atmosphere. Slip closer to Venus for another encounter. Swing past Earth for a detailed look at an inhabited planet. Then take advantage of Jupiter's gravity well to bend your path outward again. A grand tour, efficient, elegant, and mission-like. That's the story imagination tells. But orbital mechanics has its own, quieter version. Interstellar objects enter the solar system from random directions at high speeds. Once they cross the sun's sphere of influence, their trajectories curve into hyperbolas. And because planets are sprinkled along the ecliptic, some of those hyperbolic paths will, by pure chance, pass near multiple worlds. Most won't, but the rare few that do will catch our attention precisely because they look suspiciously well planned. This is the trap of pattern recognition. Out of thousands of possible orbits, we notice the one that threads multiple planets and ignore the countless others that slip past unnoticed. It's the same logic that makes a winning lottery ticket look like fate, when in reality it's just one success among millions of misses. Low probability does not equal intent. It equals rarity. Yet rarity is powerful. The first interstellar visitor baffled astronomers with its strange shape and unexplained acceleration. The second was more typical, resembling a comet we might have expected. The third now teases us with a trajectory that looks suspiciously like a flight plan. Each new visitor adds fuel to the sense that these aren't just accidents of chance, but chapters in a pattern we're too slow to see. But here's the truth hidden in the math. The trajectory of 3I Atlas doesn't require exotic explanations. The Mars flyby distance, tens of millions of kilometers, is large enough that no spacecraft designer would pick it for detailed reconnaissance. The Venus and Earth passes, while closer, still don't match the precision a mission would need. The resemblance to a tour is broad, not exact. It looks like intent only because our brains like tidy narratives. And yet, the optics remain. A visitor from beyond the stars, threading 4 planets in sequence, while official voices stay cautious and quiet. Whether coincidence or not, the effect is the same. It feels like a story. So is this mission-like path evidence of planning? Probably not, but it doesn't have to be. The mere appearance of design is enough to ignite speculation, to keep the narrative alive, and to turn an ordinary hyperbola into the most extraordinary journey we've ever watched unfold. If the path of 3I Atlas feels uncanny, there's a simple way to test whether it is truly unusual. Watch how it moves. More specifically, watch whether it follows the exact curve dictated by gravity, or whether it deviates, nudged by hidden forces. Comets are not passive stones. As sunlight heats their surfaces, gases vent into space, creating jets that act like thrusters. These forces are tiny but measurable. They can accelerate or decelerate the nucleus, subtly altering its trajectory. This is what astronomers call non-gravitational acceleration. It's ordinary cometary physics. But when applied to an interstellar visitor, the stakes rise. Because if the observed shifts don't match the outgassing we can measure, then we're left with something unexplained. The first interstellar object gave us a taste of this tension. Its path showed a small but real deviation from pure gravity, yet no corresponding gas jets were detected. The debate still echoes years later: natural venting or something else. With 3I Atlas, the opportunity is greater because it's brighter, more active, and observable for longer. That means more data and more chances to compare cause with effect. Here's the test. Astronomers track the object's position night after night, feeding coordinates into orbital models. If the coma is venting mostly carbon dioxide, the recoil force can be calculated. Multiply the gas mass escaping by its velocity, and you get thrust. Compare that thrust with the observed deviation in trajectory. If they align, the mystery collapses into physics. If they don't, the questions multiply. The first hints of irregularities already come from brightness flickers, which suggest uneven activity. If one side of the nucleus vents more strongly than the other, it could push the object in unpredictable ways. Over weeks, those nudges add up. The difference might be only a fraction of a kilometer per second. But at interstellar speeds, even small deviations become significant. The key moment will be perihelion. As heating peaks, so will the jets. If the trajectory shift matches the observed gas chemistry, the puzzle solves itself. If not, if the comet accelerates more than the venting explains, or in a direction inconsistent with the visible jets, then the door opens to more exotic interpretations. This is why astronomers are watching so closely. It isn't about proving or disproving wild theories. It's about balance sheets, input versus output, gas expelled versus motion gained. If the math balances, 3I Atlas remains a comet with quirks. If the math fails, we face the same uncomfortable question raised years ago. What else could be at play? And here's the tension. Non-gravitational accelerations are real and common, but when measured in an object from another star system, every mismatch feels amplified. Ordinary physics becomes a referendum on the extraordinary. The universe doesn't have to give us clean answers. It only has to give us data. What we choose to do with the gaps, that's the true test. Every discussion of interstellar visitors eventually circles back to the first one. Oumuamua. It appeared in 2017, raced through the inner solar system on a hyperbolic path, and vanished almost as quickly as it arrived. For a few brief weeks, astronomers scrambled to capture what data they could. What they found still divides opinion today. Oumuamua was small, so small it never showed the coma or tail expected of a comet. Instead, it reflected sunlight faintly, its brightness rising and falling in a way that implied a highly elongated shape. Some called it cigar-like, others pancake flat. The truth was, no telescope could resolve it clearly. We were watching a flicker of light and building models around shadows. Then came the strangest part, its trajectory. Oumuamua deviated ever so slightly from the path gravity alone would predict. The shift was real, measurable, and confirmed by multiple teams. But no outgassing was detected. No jets, no coma, no venting dust. A comet without the cometary behavior. An asteroid that didn't act like an asteroid. The mainstream explanation is that it was outgassing something invisible, perhaps hydrogen or carbon monoxide, that our instruments simply couldn't detect. A less exotic but unsatisfying answer. The more provocative interpretation was that it might have been artificial, a wafer-thin object, maybe even a light sail, nudged by radiation pressure rather than jets. That idea sparked headlines, books, and debates that still rage across conferences and late-night podcasts alike. What Oumuamua taught us wasn't just about interstellar objects. It was about the limits of observation. When a visitor appears unexpectedly and disappears quickly, we're left with partial data. Partial data invites imagination, and imagination fills the gaps faster than peer review ever can. 3I Atlas arrives in this shadow. It's brighter than Oumuamua, larger and cometary in appearance. Already we see a coma, gas emissions, and jets. In that sense, it feels more familiar, more explainable. But the lesson of 2017 remains. Appearances can deceive, and behavior doesn't always match expectations. If Oumuamua was a reminder of how little we know about what drifts between the stars, 3i Atlas is the test of whether we've learned from that ignorance. Will we measure its non-gravitational accelerations more carefully? Will we resist the urge to leap to conclusions before the data is complete? Or will we repeat the cycle? Anomaly, speculation, polarization. The echoes are already there. An object with unusual chemistry, flickering light curves, a trajectory threading the inner planets, silence from institutions, murmurs from the fringes. It all feels familiar because we've walked this road before. The Oumuamua lesson is simple, but difficult to live by. Don't overfit the unknown. Extraordinary explanations are tempting when data is sparse. But sometimes the mystery is not a message. It's a mirror, showing us the limits of our own certainty. As we watch 3i Atlas, the ghost of that first visitor lingers, reminding us that the line between discovery and speculation is as thin as the data we collect. And once again, the clock is ticking. Speculation thrives in the dark. When an object like 3i Atlas streaks through the solar system, its odd chemistry, strange flickers, and unusual trajectory invite bold theories. Some say it's a natural comet behaving oddly. Others whisper about probes, reconnaissance, or design. But here's the danger. Once a claim leaves the realm of testability, it stops being science and starts being story. So how do we keep claims about 3i Atlas anchored to reality? By making them falsifiable. In other words, by stating what kind of data would prove them wrong. Take the chemistry. The comet's coma looks carbon dioxide rich, almost to an extreme. The testable claim is simple. If water vapor emissions rise after perihelion, then the ratio balances, and the apparent weirdness fades into timing effects. If they don't, then the anomaly stands. Either way, the outcome can be measured with spectra in December. Take the flickering brightness. Some interpret it as breathing, an unsettling pulse. But a falsifiable claim is this. If the light curve matches the expected rotation of an irregularly shaped body, then the flickers are just geometry. If it deviates, or if outbursts occur at times inconsistent with rotation, then another mechanism is at play. Again, the prediction is measurable. Take the trajectory. It looks mission-like, skimming past 4 planets in sequence. The testable version is this. If non-gravitational accelerations from jets explain every deviation from the predicted path, then the resemblance to design is coincidence. If the accelerations are too large, too small, or misaligned with observed jets, then we're left with a genuine puzzle. Numbers, not metaphors, decide. This approach matters because history shows what happens otherwise. The first interstellar visitor left us with data so sparse that almost any model could fit it. In the absence of constraints, imagination ran wild. Light sail, alien probe, cosmic shard, none could be ruled out, and none could be proved. That vacuum of certainty left a trail of argument still unresolved. 3i Atlas is different. We have more time, more instruments, more chances to gather clean measurements. That means we can set conditions. If this, then that. And when December comes, those conditions will be met, or not. The claims will stand or fall. That's what separates science from speculation. But here's the twist. Even when claims are testable, they don't always get tested. The blackout window hides perihelion, the very moment of maximum activity. If data from Mars orbiters is limited, or if Earth-based telescopes can't reacquire quickly enough, then some of the most decisive tests may be missed. That gap will tempt some to move the goalposts, to shift from testable claim to unfalsifiable narrative. That is why discipline is needed. Every bold idea must come with a shadow, the condition under which it fails. If no such condition exists, then the idea belongs to myth, not measurement. So, as 3i Atlas sails past our worlds, the question isn't only what it is, but whether we have the patience to let data, not desire, write the ending. In late September 2025, as 3i Atlas drew closer to Mars, another story flickered across the headlines. One that, on its own, might have seemed routine. Senior US defense officials, including figures normally tethered to Washington, were suddenly called to Marine Corps Base Quantico for an unusually large, short-notice gathering. The public record on this event is thin, but clear. News agencies reported the meeting. The Pentagon acknowledged it happened. The White House press office fielded questions and described it in the most generic terms possible: strategic discussions and ongoing readiness. There were no photos of smiling officials shaking hands, no glossy press packets, no agenda released to the public. It was acknowledged, not advertised. Observers noted two things about this meeting that stood out. First, the size. It wasn't a handful of staffers huddling in a secure room. It was a broad gathering of top brass. Generals, admirals, senior civilian leaders. The kind of lineup usually reserved for major reviews or crises. Second, the timing. It coincided almost exactly with 3i Atlas approaching its closest point to Mars. To be absolutely clear, no evidence links the two. The meeting could just as easily have been about fiscal year planning, conventional conflicts, or personnel changes. Military leadership meets often, and the reasons aren't always shared. What made this particular gathering unusual was not its existence, but the optics. Large, sudden, secretive, and vague in explanation. That combination is fertile ground for speculation. When an extraordinary object streaks through the solar system, at the same moment an extraordinary meeting unfolds behind closed doors, people connect the dots, even if the dots aren't meant to be connected. The narrative forms itself. What did they know, and why weren't they saying more? Publicly, that's as far as the facts go. A meeting happened. It was bigger than usual. The official explanation was vague. The timing was coincidental with 3i Atlas's Mars encounter. Everything else, the motives, the agenda, the whispers about space, is conjecture layered on top of those bare details. And yet, perception is as powerful as fact. For those following 3i Atlas, the silence from NASA and ESA already felt conspicuous. Adding a mysterious defense meeting into the mix sharpened that feeling. Institutions were gathering, but not sharing. Eyes were watching, but words were scarce. The effect was not proof of anything hidden, but it was fuel for the story. That's what happened publicly. A meeting confirmed, acknowledged, and quickly waved away. The lack of detail didn't close the conversation. It opened it. Because when official words shrink, speculation expands to fill the void. Humans are pattern seekers. We look at random stars and see constellations, at scattered footprints, and invent a path. When two events happen close together in time, our instinct is to draw a line between them. The meeting at Quantico in late September and the passage of 3I Atlas past Mars are perfect fuel for that instinct. On paper, they're unrelated. One is a celestial object sweeping through the solar system on a hyperbolic trajectory. The other is a closed-door gathering of defense leaders. No official has ever suggested a link. No document ties the two together. And yet, for many following the story of 3I Atlas, the overlap feels too sharp to ignore. A rare interstellar visitor, a rare, sudden military meeting, both within days of each other. It's the same mental reflex that drives conspiracy theories, but also the same reflex that fuels scientific discovery. Sometimes the connection is real, Kepler noticing the link between orbital periods and distance. Sometimes it's illusion, imagining canals on Mars that turned out to be optical tricks. The line between insight and illusion is razor thin. In this case, the temptation to connect dots is amplified by silence. NASA speaks in technical updates. ESA posts cautious FAQs. The military meeting is described in vague phrases like strategic discussions. None of these institutions are lying, but none are painting a vivid picture either. That restraint leaves room for imagination, and imagination is rarely restrained. The narrative that forms is obvious. The military knows something about 3I Atlas, and that's why they gathered. Maybe they saw its trajectory as threatening. Maybe its unusual chemistry sparked classified interest. Maybe it isn't natural at all. None of these claims are evidenced, but once the dots are placed, the line practically draws itself. The irony is that ordinary explanations are just as plausible. The fiscal year was ending. Budgets and priorities needed to be set. Global tensions were high. Defense leaders had urgent matters beyond the stars. A senior officer could have retired, triggering succession planning. These explanations lack the drama of a space connection, but they fit the data just as well, perhaps better. Yet, the human brain doesn't crave boring answers. It craves coherent stories. A comet from another star system appearing in the skies at the same time. Generals convene in secrecy. That's not just coincidence, it's a plot line. And in the age of social media, plot lines spread faster than press releases. The temptation to connect dots isn't proof, it's perception. But perception has power. It shapes how people interpret silence, how they question institutions, how they frame the unknown. Even if Quantico had nothing to do with 3I Atlas, the pairing of those events has already become part of the mythology surrounding it. And once dots are connected in the public mind, no official denial easily erases the line. Not every mystery demands an extraordinary answer. In fact, most don't. When it comes to the Quantico gathering, there are plenty of down-to-earth explanations, ordinary on the surface, but with enough gravity to explain the urgency without invoking visitors from another star. Start with the calendar. Late September is the end of the US government's fiscal year. Budgets close, priorities reset, and leadership teams meet to align strategies for the coming cycle. These are not casual conversations. They involve billions of dollars, long-term deployments, and shifts in force readiness. A large, short-notice meeting may simply have been about money, planning and paperwork, but paperwork that shapes the backbone of military power. Then there's the geopolitical backdrop. In multiple regions, from Eastern Europe to the South China Sea, tensions have been simmering. Joint chiefs and senior officials don't gather in person unless there's a pressing need to coordinate responses across commands. A sudden uptick in activity abroad, or intelligence reports pointing to escalation, could have been more than enough to justify a high-level huddle. To the public, ongoing readiness sounds bland. Inside the room, it could have meant scenarios that would dominate headlines if they surfaced. Personnel is another possibility. Senior military careers turn on retirements, promotions, or sudden health changes. Leadership transitions demand secure, face-to-face coordination, especially if the roles involve nuclear command, cyber defense, or space operations. What looks from the outside like a mysterious meeting could, in fact, have been about continuity at the very highest levels of command. And yet, these mundane explanations don't erase the mystery, they sharpen it, because none of them are mutually exclusive with the speculation about 3i Atlas. If the gathering was about budgets or global tensions, officials could say so more clearly. Instead, the public got vague phrases, and vagueness is oxygen for speculation. This is where mundane explanations still have teeth. A budget review may not stir the imagination, but it can be classified if it involves future technologies or sensitive intelligence. A routine readiness meeting may conceal details about war games, cyber vulnerabilities, or intelligence briefings too sensitive to share. A leadership transition could mask delicate negotiations over policy shifts. These are not glamorous stories, but they are weighty, serious, and often more consequential to everyday life than anything happening millions of kilometers away. So, when people ask, why so secretive? The simplest answer may be, because secrecy is built into the system. Not to hide alien contact, but to shield negotiations, technologies, or intelligence that can't safely be aired. The opacity may not mean extraordinary, it may mean ordinary, but important. And that's the paradox. The explanations most likely to be true are also the ones least likely to satisfy. They don't have drama, they don't have cosmic stakes, but they have teeth, because budgets, conflicts, and leadership shifts can change the world far more directly than a comet ever will. Still, the silence ensures the extraordinary story survives alongside the ordinary ones. And in the battle between the two, perception usually crowns the winner. The thought lingers. What if the Quantico meeting wasn't about budgets, geopolitics, or personnel at all? What if it really did have something to do with 3i Atlas? The idea appeals because it ties the extraordinary in the sky to the extraordinary behind closed doors. But if that were true, what signs would we expect to see? First, coordination across agencies. A space-related briefing wouldn't stop at the Pentagon. It would involve NASA, the US Space Force, intelligence agencies, and probably international partners. If the subject were truly 3i Atlas, we'd expect to see unusual cross-communication, subtle but noticeable, between civilian space scientists and defense organizations. Sometimes that shows up as sudden delays in data releases or unexplained pauses in public mission updates. Second, classified sensors. The military already tracks space with radars and satellites far more sensitive than anything the public hears about. If 3 Atlas displayed unexpected behavior, accelerations, emissions, or structural changes, those sensors would be tasked to watch it. We wouldn't see the raw data, but we might see hints, carefully worded briefings that sound more evasive than informative, or acknowledgements that monitoring is ongoing without details. Third, the radio spectrum. If the object were emitting signals, natural or not, radio astronomers worldwide would notice, and so would defense monitoring stations. A genuine detection would be almost impossible to keep contained. The more people listening, the harder it is to keep silent. The absence of unusual radio chatter is telling. It suggests no such signal has been detected, or at least none compelling enough to set off alarms across the scientific community. Fourth, posture. If defense leadership believed 3i Atlas posed even a remote threat, we would expect to see a change in readiness levels. Subtle, yes, but visible in things like satellite taskings, classified budgets, or sudden briefings to lawmakers. Space is global. Secrecy has limits. The more urgent the risk, the harder it would be to hide. Finally, leaks. Modern science is too distributed, too international to keep a discovery of that scale sealed. A detection of artificial propulsion or emissions wouldn't just sit in a vault. It would ripple across universities, observatories, and preprint servers. Silence in that sphere suggests that, whatever 3 Atlas is, it isn't broadcasting anything too extraordinary. This doesn't mean the Quantico meeting wasn't space-related. It means that if it were, we'd expect ripples far wider than one vague gathering. Evidence would leave fingerprints. Even when governments try to hold secrets, the sheer number of eyes and instruments aimed at the skies makes a total blackout unlikely. And that's the irony. The absence of those signs is itself a sign. If the meeting was truly about 3i Atlas, the story would already be leaking through cracks in the system. Instead, we're left with coincidence, silence, and speculation. Which means the more sober conclusion is the simplest one. If there was a link, we'd see smoke. So far, there's no smoke, only shadows. In the absence of facts, coincidences can feel like proof. The September timing of 3i Atlas near Mars and the sudden Quantico gathering is a perfect example. 2 unrelated events, close together in time, become fused in the public imagination. The human brain hates randomness. It prefers order, even if that order is invented. This reflex is powerful. It's why gamblers believe in hot streaks, why investors see patterns in stock charts, and why ancient cultures drew stories into the stars. The mind treats proximity as connection. When A and B happen side by side, it insists that A must have caused B, or at least that they belong to the same story. Applied to 3i Atlas, this creates a feedback loop. The comet already feels unusual. Its chemistry strange, its behavior irregular, its trajectory eyebrow-raising. At the same moment, the military does something unusual too. Put those two together, and suddenly each event amplifies the mystery of the other. The story no longer reads as 2 coincidences, it reads as one conspiracy. The problem is that coincidences are inevitable. In a world of billions of people, thousands of meetings, and countless astronomical events, overlaps will happen. Some will look meaningful, even when they aren't. Statistically, it would be stranger if they didn't. Yet our minds rarely accept that. We lean into the story, not the statistics. That doesn't mean all coincidences are meaningless. Sometimes they do point to hidden links. History has examples. A spike in respiratory illness coinciding with a contaminated water pump, or unusual seismic signals paired with volcanic eruptions. Those patterns reveal truths. But what separates those from illusion is data, evidence that can be tested, measured, reproduced. In the case of 3 Atlas and Quantico, no such evidence exists. The link is timing, and timing alone. Treating that as proof risks collapsing speculation into belief, belief into narrative, and narrative into rumor. Once that happens, the rumor takes on a life of its own. Every new silence from NASA, every vague quote from officials, gets folded back into the storyline as if it were confirmation. Coincidence hardens into evidence, and evidence hardens into conviction. This is why disciplined skepticism matters. Not cynicism, skepticism. The difference is crucial. Cynicism dismisses mysteries as nonsense. Skepticism acknowledges the intrigue, but demands that claims remain falsifiable. If the Quantico meeting was about 3i Atlas, there should eventually be data, leaked agendas, corroborating statements, unusual sensor reports. If none appear, the coincidence should be treated as just that, an overlap, not a link. Yet here lies the paradox. Even if evidence never comes, the coincidence will live on in the story of 3i Atlas. Because stories don't follow the rules of statistics. They follow the rules of narrative. And in narrative, a meeting in Quantico at the same time as a comet flyby will always look like more than chance. Coincidence isn't evidence, but in the public mind, it often plays the same role. Not long ago, astronomy was the domain of massive observatories perched on mountaintops, controlled by institutions with budgets that stretched into the billions. If you wanted to know what was happening in the night sky, you waited for the data those institutions chose to release. Today, that monopoly has cracked. The tools of discovery are cheaper, smarter, and everywhere. A decent consumer telescope with automated tracking and a sensitive digital camera can now capture faint comets, even ones streaming in from interstellar space. Image stacking software turns noisy frames into crisp signals. Networks of robotic telescopes, some run by universities, others accessible by subscription, let amateurs book observation time in Chile, Hawaii, or Australia from a laptop at home. The sky has become decentralized. That shift matters for 3i Atlas. Because while NASA and ESA drip-feed cautious updates, amateurs are already capturing raw images night after night. On forums and social media, they share time-lapses, brightness curves, and spectral readings that look almost professional. Some of these observers coordinate across continents, pooling data into light curves that rival institutional outputs. Others simply post what they see: faint plumes, irregular flickers, strange structures. Not all of it is reliable. One person's sunward jet may be another's tracking error. A sudden brightening might be an outburst, or just a cloud crossing the frame. Without calibration, without rigorous reduction, noise can masquerade as signal. But mixed among the artifacts are genuine observations, and those observations spread fast, unfiltered by press officers or review committees. This is the paradox of democratized telescopes. The data is more open than ever, but the truth is harder to pass. In the institutional model, credibility came from authority. In the decentralized model, credibility comes from cross-checking. If 3 observers on different continents capture the same flare at the same time, it's real. If only one posts it, it's noise. Truth becomes consensus, built from the ground up, not pronouncement handed down. For an object like 3i Atlas, this shift is profound. It means no single agency controls the narrative. If something unusual happens during the blackout window, there's a good chance someone, somewhere, will have a telescope pointed at it. And if they share the data online, the world will see it before institutions can decide how or whether to frame it. But there's risk in that freedom. Amateur data is uneven. Some reports will be sensationalized. Some images will be manipulated. And in the race to interpret, the loudest voices often drown out the most careful ones. Decentralized truth is fast, but it is also messy. Still, this is the new reality. The mystery of 3 Atlas isn't just unfolding in observatories and mission control centers. It's unfolding in backyards, school clubs, and online forums. 1,000 lenses are pointed skyward, and together they form something powerful, a collective watch that no single institution can silence, and no single narrative can fully control. With 3i Atlas, there is no shortage of images. Every night, observers across the globe upload raw frames, stacked composites, and brightness measurements. Some of these datasets are careful, calibrated, and scientifically valuable. But in the rush of sharing, good data often sinks beneath louder, less reliable claims. The problem isn't scarcity, it's noise. A properly reduced image showing a faint, symmetric coma rarely goes viral. A distorted frame with a dramatic streak labeled sunward jet races across social feeds within hours. Careful notes about exposure times and filters don't spark debate. A single screenshot with ominous music does. The internet rewards spectacle, not rigor, and spectacle often buries the truth beneath layers of misinterpretation. Take the brightness curves. Teams of amateurs, working with consistent methods, have been compiling light curves that track 3i Atlas's changing intensity. These records matter. They tell us when outbursts occur, whether jets are stable or episodic, whether the nucleus is rotating. But outside small circles, almost nobody sees them. What the public sees instead are cherry-picked images, frames showing sudden spikes or unusual angles, stripped of context, passed around as evidence of anomalous activity. Even legitimate phenomena get distorted. Anti-tails, projection effects, or faint companion fragments appear in the data, but without explanation, they become proof of exotic theories. What should be a teaching moment about comet dynamics becomes a headline about alien propulsion. The careful explanation, geometry, dust, scattering, travels slowly. The sensational misread travels instantly. Institutions don't help. NASA and SA post updates, but in dry, technical language. Without context, the public turns elsewhere for interpretation. The amateurs willing to dramatize their findings gain the largest audiences, while those posting carefully processed, reproducible data are drowned out. The result is an information inversion. The best data circulates quietly. The worst claims dominate loudly, and those trying to follow along are left in confusion. This doesn't mean the good work is wasted. In astronomy, reproducibility is the final arbiter. If 3 different observers, using different instruments, record the same spike at the same time, it's real. If one observer alone claims it, it's noise. The problem is that by the time careful cross-checking happens, the viral claim has already shaped the narrative. The truth emerges, but often too late to erase the story. 3i Atlas is a perfect storm for this dynamic. It's faint, hard to observe, and slipping into a blackout window. The professionals release little. The amateurs release much. And in the scramble, the signal gets buried under noise. That's why the object has become more than just a comet. It's also a mirror for how we process information in the 21st century. The best data is out there, but to find it, you need patience, skepticism, and the willingness to dig beneath the headlines. Otherwise, the noise wins, and the real story of 3i Atlas risks being lost in the very moment it matters most. When people debate the mystery of 3i Atlas online, one theme comes up again and again. The orbit. Screenshots of tables filled with numbers, distances, speeds, elongations, get posted as proof of hidden truths. But those tables, called ephemerides, are tools that require care. Read them wrong, and you can turn normal celestial mechanics into something that looks extraordinary. An ephemeris is simply a list of where an object will be at a given time. It tells you how far the comet is from the Sun, r, how far from Earth, d, and at what angle it sits from the Sun in our sky, elongation. It can also include the phase angle, the tilt, the brightness estimates, and more. To a trained eye, these numbers sketch out the comet's motion in 3 dimensions. To the untrained eye, they can look like riddles hiding secrets. Take distance. A value of 0.9 astronomical units might sound tiny and threatening if you don't know that it equals about 30 million kilometers, a wide miss by any standard. Or take elongation. When it falls below 20 degrees, Earth-based telescopes struggle because of the sun's glare. To some, that reads like a cover-up. Why aren't we looking when it's closest? In truth, the numbers explain the blackout window. Physics, not policy. Brightness is another trap. Ephemerides list predicted magnitudes, but those are estimates based on assumptions about how active the comet will be. If 3i/Atlas outbursts or dims unexpectedly, the real brightness can diverge from the prediction. That divergence isn't evidence of a hidden force. It's evidence of the uncertainty baked into the model. Yet online, the difference between prediction and reality often gets framed as anomaly. Even small details can mislead. Negative signs in inclination values, rounding errors in orbital eccentricity, or the choice of coordinate system can create apparent inconsistencies when data from one source is compared with another. To someone not used to reading orbital mechanics, the inconsistencies look suspicious. To those who work with ephemerides every day, they're just quirks of notation. This is why context matters. An ephemeris is a forecast, not a revelation. It evolves as new measurements refine the orbit. What looks like a dramatic change is usually just improved accuracy. When amateurs mistake these refinements for hidden adjustments, the narrative drifts away from science and into suspicion. The tragedy is that ephemerides are powerful tools. Anyone can plug the data into software, generate sky charts, and predict when the comet will rise and set from their location. They allow distributed observers to coordinate, to test predictions against reality. Used well, they democratize astronomy. Used poorly, they feed myths. For 3i Atlas, the lesson is simple. Don't treat the numbers as magic. Treat them as evolving guides. Understand the limits, the assumptions, the uncertainties. Otherwise, you risk turning a natural comet into a manufactured mystery, burned not by sunlight, but by misread tables. When the public can't get official images, a vacuum forms, and vacuums attract noise. One of the most toxic forms of that noise is the fake leak, an image, a file, or a snippet that claims to be secret but is either misattributed, doctored, or outright invented. For a story like 3i Atlas, the fake leak playbook follows a predictable script. Knowing the script helps you spot the fakes before they become folklore. Step 1. Plausibility dressing. A fake leak looks real because it borrows the look and language of authenticity. Instrument headers, mission timestamps, cryptic metadata, or the bland bureaucratic phrasing people expect from agencies. The document may even mimic the font and template of a mission page. For most viewers, those details signal authority, and their presence short-circuits skepticism. Step 2. Selective ambiguity. A fake leak includes enough detail to be convincing, but leaves key things out. Full metadata, precise coordinates, calibration frames, or corroborating observers. That ambiguity makes verification hard and invites people to fill gaps with imagination. The less specific the claim, the harder it is to debunk quickly, and the longer it has to spread. Step 3. Emotional framing. Fake leaks are packaged as revelations. Official image, withheld, what they don't want you to see, classified frame, paired with ominous music or blunt headlines. Even a mediocre image can become astonishing. Emotional framing turns curiosity into moral outrage, and outrage spreads faster than careful analysis. Step 4. A single source push. The initial post often comes from an anonymous account, a forum thread, or a private channel. It then gets amplified by influencers who may not verify anything but know what makes views. Once the post reaches a few high-traffic accounts, replication looks like corroboration, and the claim gains apparent credibility simply through repetition. Step 5. Defensibility by mystery. When challenged, fake leak spreaders exploit the same silence that feeds suspicion. Why hasn't it been debunked, they ask. Why won't the agency respond? The answer usually is, because the agency doesn't chase every rumor, and because official channels don't want to amplify false claims. That refusal to engage is spun as tacit confirmation. So, how do you avoid being taken in? First, check provenance. Real mission images include detailed metadata, timestamps tied to known instruments, exposure details, and calibration frames. If those are missing or suspicious, so is the image. Second, look for independent corroboration. Did multiple observatories record the same feature at the same time? If not, treat the claim with skepticism. Third, prefer raw data over processed composites. Processing can create artifacts, Raw frames let you see whether something is an instrument effect or a genuine structure. Fourth, consult expert commentary from established teams before trusting viral posts. Experts won't always reply on social media, but their published analyses and community channels are where verification usually appears. Finally, remember motive. Fake leaks are often designed to attract attention, clicks, donations, or followers. Some are hoaxes, others are honest mistakes amplified by hype. Either way, the method is the same. Dress up a claim in the trappings of secrecy so it feels weighty and real. In the blackout around perihelion, the temptation to believe increases, because official silence makes the fake more plausible. That's why media literacy matters most exactly when the sky gives us the least. If you want to follow 3i Atlas responsibly, learn the playbook, demand provenance, and let data, not drama, decide what you trust. The loudest stories about 3i Atlas thrive on spectacle, strange tales, hidden signals, secret meetings. But the most decisive evidence rarely looks spectacular. It looks boring. A string of numbers, a flat line on a chart, a null result buried in a technical circular. Yet time and again, it's this kind of mundane data that dismantles the most dramatic claims. Consider brightness measurements. When a viral image circulates claiming a sudden outburst, the natural reaction is awe. The comet flared. Something extraordinary happened. But then, a network of amateurs posts their photometry curves, carefully reduced and plotted across multiple nights. The curve is steady. No spike, no burst. Just the expected slow brightening as the comet nears the sun. The boring data breaks the claim. Or think about astrometry, the precise coordinates of the object in the sky. A dramatic video might insist the comet changed course. But when hundreds of observations from around the globe are plotted, the points fall neatly along the predicted hyperbolic path. No deviation, no hidden propulsion, just celestial mechanics doing exactly what it should. Again, boring data erases the drama. Spectroscopy offers another example. Viral posts might suggest exotic emissions, strange chemical signatures, even artificial signals. Yet, when professional teams publish their spectra, the lines are exactly where they should be. Carbon dioxide, carbon monoxide, faint traces of sulfur compounds. No mystery frequencies, no unexplained features, just the chemistry of frozen volatiles warmed by sunlight. This is the paradox of modern astronomy. The strongest evidence is often the least shareable. A graph showing a smooth curve doesn't spark excitement. A PDF full of tables doesn't trend on social media. But in science, consistency is power. The flat line is the answer. The absence of anomaly is itself the result. And yet, boring data doesn't always win the narrative war. Spectacle drowns out sobriety. A misleading image can circle the world in hours, while careful cross-checks may take days to compile. By the time the null result arrives, the myth has already hardened. The comet breathed, the comet veered, the comet signaled, even if the data proves otherwise. This is why responsible watchers of 3 Atlas emphasize patience. Wait for multiple observers. Wait for reduction. Wait for replication. If 3 independent datasets say the same thing, trust the consensus. not the clip. Extraordinary claims rarely survive ordinary scrutiny. But scrutiny takes time. In a sense, the boring data is the hero of this story. It's the shield against imagination run wild, the quiet force keeping the mystery within the bounds of nature. Every time a viral claim dissolves under the weight of flat curves and predicted coordinates, the comet becomes less a harbinger of the unknown and more what it truly is, an alien traveler obeying familiar laws. So when the noise peaks during the blackout window, remember this: the truth of 3i Atlas won't come from the loudest posts. It will come from the quiet graphs, the flat lines, and the numbers that refuse to bend. If you're wondering why NASA or ESA haven't turned 3i Atlas into a media spectacle, the answer lies less in secrecy and more in culture. Space agencies are institutions, and institutions remember their mistakes. That memory creates what might be called error aversion, a deeply ingrained instinct to move slowly, speak cautiously, and avoid claims that might unravel later. The scars run deep. In 2012, a high-profile announcement claimed scientists had discovered arsenic-based life in a California lake. Headlines screamed about a new form of biology, a rewriting of the rules of life itself. Months later, replication efforts failed, and the claim collapsed under scrutiny. The backlash was brutal, and the credibility of both NASA and the researchers took a hit. Years before that, a hint of faster-than-light neutrinos from CERN electrified the world, only to be traced to a loose cable in the detector. The excitement turned into embarrassment. These episodes taught institutions a hard lesson. Moving too fast can be worse than moving too slow. Better to say little and be correct than to promise everything and retract later. And so the communications pipeline tightened. Every statement is now filtered, reviewed, cross-checked. Bold claims require extraordinary evidence, and extraordinary evidence takes time to gather. 3i Atlas falls into this trap perfectly. On paper, it's one of the most exotic things we've ever seen. A body from another star system threading through the inner solar system, rich in strange chemistry, passing near multiple planets. The temptation to hype it is enormous. But the data is still evolving. The nucleus size is uncertain. The chemistry may change post-perihelion. The orbital refinements are ongoing. For an institution, every one of those uncertainties is a risk. Speak too soon, and you might be wrong. So, instead of dramatic briefings, we get blog posts. Instead of countdown clocks, we get updates tucked away in technical circulars. For the public, this feels like silence. For the institution, it feels like responsibility. Better to undercommunicate than to overpromise. There's also the peer review bottleneck. Institutional scientists don't just want to share. They want their results vetted, checked, published in journals. That process takes months, sometimes years. But comets don't wait for peer review. They blaze across the sky, vanish, and leave their mysteries behind. The tension between cosmic timelines and academic timelines guarantees a communication gap. Error aversion isn't conspiracy, it's self-preservation. A single overstatement can haunt an agency for years. But to outsiders, the restraint looks like suppression. The blackout window magnifies that perception. Just when the comet is most interesting, Earth goes blind, and the agencies fall silent. From inside, it's caution. From outside, it's fuel for suspicion. That's the paradox. The very caution designed to protect credibility may, in fact, erode trust. The public doesn't see prudence, they see avoidance. And in that gap, speculation takes root. Atlas isn't just testing our science, it's testing the fragile relationship between institutions and the public they serve. When people imagine NASA or ESA, they picture sleek spacecraft, dazzling images, and the thrill of discovery. What they don't picture is the endless chain of approvals, sign-offs, and interagency coordination that controls what gets said and when. Yet for something like 3I's Atlas, that bureaucratic machinery is often the loudest force in the room, even louder than the comet itself. Every public statement passes through layers. A scientist drafts an update. A communications officer rewrites it into plain language. Legal reviews it to make sure there's no overpromise or liability risk. International partners weigh in so that messaging aligns across agencies. By the time the post emerges, days or weeks have passed. And because each stakeholder has veto power, the final product tends to be stripped of drama and nuance. What remains is the dry, technical blog post, safe, correct, and uninspiring. This lag doesn't matter much for routine missions. A satellite maneuver, a rover milestone, a calibration update. None of these are urgent to the public. But with 3I Atlas, the comet is on the move. Its behavior changes week by week. By the time a carefully cleared statement appears, amateurs have already posted raw images, speculators have already spun theories, and the narrative has sprinted far ahead of the institutions. There's also the burden of coordination. NASA isn't alone in this. The European Space Agency, the Minor Planet Center, ground-based observatories, and even university teams all contribute to the record. To avoid contradictions, they coordinate messaging. But coordination across continents means delays. A blog post isn't just a blog post, it's a negotiated document between multiple bureaucracies. Add funding politics to the mix, and the pace slows further. Space agencies live under constant scrutiny. Budgets depend on credibility. If a bold statement about an interstellar comet later proves wrong, it can haunt funding hearings for years. Safer, then, to wait until the numbers are unimpeachable. The culture bends toward delay, not because the science isn't exciting, but because bureaucracies fear the consequences of haste. The irony is sharp. The institutions designed to discover and explain the universe often find themselves last in line to narrate it. The tools are cutting edge, the communications pipelines are glacial. And into that gap step, the amateurs, the influencers, and the conspiracists moving at the speed of social media. This isn't incompetence, it's structural. Large organizations cannot move faster than their review chains allow. But when the sky is moving at 61 kilometers per second, bureaucracy feels like silence. And silence, in turn, breeds suspicion. In the case of 3 Atlas, the bureaucracy's instinct to wait and coordinate may protect against embarrassment, but it also hands the story to others. The comet becomes less about what it is and more about who dares to speak first. The question keeps surfacing. If 3I Atlas is just a comet, why do some people suspect the military might be involved? The answer isn't a secret spacecraft or hidden signals. It's the overlap, the grey zone where classified monitoring meets civilian science. Modern astronomy doesn't happen in isolation. Space surveillance networks, many operated by defense agencies, are constantly tracking objects near Earth. Radar systems, missile warning satellites, and classified telescopes watch the sky as part of national security. When something unusual enters the solar system, whether a defunct satellite, a stray rock, or an interstellar visitor, those systems see it too. But unlike NASA or ESA, they don't publish press releases. Their data is locked behind clearance walls. That doesn't mean a cover-up. It means two parallel streams of observation exist. One is open, peer-reviewed, slow, and public. The other is fast, sensitive, and hidden. Sometimes the streams converge when military radar helps refine an asteroid's orbit, or when classified sensors quietly hand off tracking data to civilian agencies. But the details of those handoffs rarely make the news. The military doesn't want adversaries to know the limits of its eyes in the sky. 3i Atlas lands squarely in that overlap. Civilian astronomers track its position with optical telescopes. Space agencies plan observation campaigns. But it's almost certain that defense systems are watching too, if only because anything with a hyperbolic trajectory gets flagged. That doesn't mean anyone suspects it's artificial. It just means the military monitors anomalies by default. This is where perception splits. For institutions, coordination is routine. Classified sensors supplement open data. Analysts compare notes, and then only the unclassified results are published. For the public, that silence feels loaded. If the military knows more but isn't saying, then speculation fills the gap. The phrase, "they're hiding something," thrives in that void. The truth is more banal, but no less fascinating. Classified programs may detect details, thermal signatures, unusual jet dynamics, precise acceleration, that won't be shared, not because they're shocking, but because revealing them could expose sensitive technology. You don't announce that your surveillance satellite saw a gas jet at 2:17 a.m. if it also reveals your satellite can detect faint heat signatures from millions of kilometers away. The classification isn't about the comet, it's about the sensor. This structural silence creates a feedback loop. Civilian science waits for enough public data to publish. Military programs hold back their superior data to protect capabilities. In the gap, narratives bloom, sometimes wild, sometimes reasonable, always hard to disprove. So when people whisper that 3i Atlas must be classified, the reality is subtler. It's not the object that's classified, it's the tools that watch it. And that difference between what is seen and what is said keeps the mystery alive, not because of alien secrets, but because of the inevitable collision between open science and hidden security. When it comes to 3i Atlas, the loudest argument in online debates is not about what we know, it's about what we don't know. People point to the lack of press conferences, the gaps in data, the missing images from perihelion, and conclude, something must be hidden. But this reasoning confuses two very different things. The absence of evidence is not the same as evidence of absence. In other words, just because an agency hasn't shown us something, that doesn't prove the something exists or doesn't exist. It simply means the window is empty. Maybe the instruments couldn't observe during the blackout. Maybe the results are still being processed. Maybe nothing unusual happened at all. silence is not a verdict. It's just silence. The danger is that human brains hate silence. We're pattern-seeking machines. If a gap opens, we fill it. A missing image becomes a withheld image. A delayed report becomes suppressed data. A lack of commentary becomes proof of conspiracy. The vacuum of information doesn't stay a vacuum for long. It gets filled with stories. And those stories, once circulating, harden into belief. History offers plenty of examples. During the early days of spaceflight, when telemetry blackouts occurred as spacecraft passed behind the moon, speculation ran wild. Every gap was an invitation for myth. The same dynamic played out with Oumuamua in 2017. The strange acceleration could have been explained by outgassing, but no outgassing was directly detected. The absence of clear evidence for one explanation fueled the belief in another, more exotic one. 3I Atlas now sits in that same ambiguous space. The CO2 dominance is strange, but not unprecedented. The flickering brightness is unusual, but consistent with patchy jets. The trajectory is interesting, but not necessarily intentional. Each of these features has plausible natural explanations. But the gaps, the places where evidence is missing or delayed, become magnets for speculation. And speculation often outruns the data. This doesn't mean that suspicion is irrational. It means it's incomplete. In science, the absence of data is just that, a missing puzzle piece. It doesn't tell you what the piece looks like, only that it's not on the table yet. The real discipline lies in resisting the urge to color it in prematurely. For 3I Atlas, the months ahead will test that discipline. As new observations emerge post-perihelion, some claims will dissolve under the weight of data. Others may persist, not because the evidence supports them, but because belief no longer needs it. Once a story takes root in the absence of evidence, evidence itself often struggles to catch up. That is the irony. The void left by institutional caution is filled by imagination, and imagination is sticky. The only antidote is patience. To remember that not seeing isn't proof of hiding, and not knowing isn't proof of knowing the worst. In the case of 3I Atlas, the silence may be frustrating, but it should not be mistaken for revelation. By December, the blackout will end. Earth's telescopes will swing back toward 3I Atlas, clear of the sun's glare, and the flood of new observations will begin. The question is, how do we, as watchers, avoid turning that flood into another storm of confusion? The only responsible way is to prepare now, not for revelations, but for reality. First, temper expectations. When Earth regains its view, the most likely outcome is not a revelation of alien design, nor proof of impossible physics. It's data, spectra of gas ratios, light curves of activity, astrometric positions pinned down with better precision. These will confirm, refine, or even erase some of the anomalies debated during the blackout. But they won't read like headlines. They'll read like numbers, and that's the point. Second, be patient with process. December data won't arrive all at once. Observatories will release early frames, yes, but full analyses take weeks to reduce, calibrate, and cross-check. The first images may look ordinary, just a faint blur with a tail. The richness comes later, when dozens of teams compare results and the patterns emerge. Responsible watching means resisting the urge to declare conclusions on day one. Third, trust replication, not single claims. If one observatory reports an unusual jet orientation, wait to see if others confirm it. If one telescope sees a brightness spike, look for corroboration. In astronomy, truth lives in convergence. December will bring plenty of data. The challenge will be filtering for consistency, not novelty. Fourth, be skeptical of noise disguised as revelation. The blackout will have primed people for the big reveal. That makes December a fertile ground for fake leaks, misattributed images, and sensational misreads of early data. The responsible stance is not to dismiss everything, but to demand receipts, timestamps, metadata, cross-checks. If a claim survives scrutiny, it deserves attention. If it doesn't, it deserves to fade. Finally, keep perspective. Three-Eye Atlas is historic, not because it might be artificial, but because it's real. An interstellar object threading through our system, carrying the chemical fingerprint of another star's nursery. That alone is extraordinary. December gives us the chance to study that fingerprint more closely, to see how the alien ice responds to our sun, to add one more data point to the still young science of interstellar visitors. That's enough wonder without gilding it with fear. The responsible way to watch December is to see it as a test, not of the comet, but of us. Can we hold curiosity without collapsing into certainty? Can we wait for evidence instead of feeding on rumor? Can we treat silence as space for patience instead of proof of conspiracy when the telescopes open their eyes again? We'll find out. The comet will show us what it is. The question is whether we'll be ready to see it clearly, without drowning it in the noise we've created ourselves.